last time we were talking about functions. We were talking about injective, surjective, and bijective functions. And we said that the function was injective if it was one-to-one, surjective if the function is onto, and then bijective if the function is both one-to-one and onto. In fact, let's say this first example, let's say this went on, all the way down here. It looks like it's going to cover all the y values going up and down. So it looks like that one is onto because it's going to cover all the values in the codomain. So it looks like this is onto, but it's not one-to-one because, and I'll just take one example. You can see this point right here came from two different x values. Like, for example, let's say this function value here is maybe 8. You see that two different x values produce that same function value. And actually, if you go over here, really 3 produce that same function value. So this function looks like it's not one-to-one. And let's say if we assume that this is going to, say, keep going down forever and keep going up forever, it looks like this one is onto because it looks like we're going to cover all the values of y. And it looks like it's one-to-one because no y value is produced by more than one x value. Because if you look at all these values here, they only came from one x value. And of course, also to test for one-to-one, we can use the horizontal line test. We have to start at the top and go down. If the curve passes the horizontal line more than once at any point, that means it's not one-to-one. In fact, you can see right here, it's passing it a couple of times. The curve is passing a horizontal line here, here, and here. And actually, there's several places like that. But if it happens even once that our curve passes a horizontal line more than once at any place, then it's not one-to-one. Now, if we go down here, notice the horizontal line is never crossed more than once by our curve. So this function is one-to-one. Now, if you take, say, the sine function, and this isn't drawn too well, but you can get the idea that this is the sine, you'll notice, of course, the sine function, if you let it go all the way out, it's not going to be one-to-one because, again, it crosses horizontal line more than once. If that happens at any place, like I said, I'll just pick one place. If this was the only place here where it crossed more than once, where it crossed a horizontal line more than once, then that would be enough to say that it's not one-to-one. And also, you can see that it doesn't cover all the y values. If our codomain is, say, all real numbers, you can see it doesn't get anything above this or below this. So this is also not onto. And let's take a look at one more fancier example here. Let's say if we look at this function here, this piecewise function, it says from negative infinity to -1, it's the line y equals x plus 2. So it'd be this line here. And then between -1 and 1, it's the curve y equals x squared, which is a parabola. And then from 1 to infinity, it's going to be the straight line y equal x, which is just this. I probably should have made one of these not equal. Let me fix that. So like something like, excuse me, that should be, what am I doing here? Sorry. This should be -1, like that. So this function, you can see, and it looks like it's going to cover all the possible y values from -infinity to infinity. So it looks like this function is onto, but clearly it's not 1-to-1, because you can just pick that right there. You can see the curve cross our horizontal line in 2 places. So this is not 1-to-1. And again, to use our fancier terms, we can say it's not an injection, or not a injective, you want to say it that way, but it is, the function is surjective. And definition, if f a to b is a bijection of a onto b, then the function g defined this way, b a b cross a such that a b is in f is a function on b into a. This book sometimes uses the word into. That's not a very common thing, though. They just sort of mention every so often, but they'll use into it. So I guess this is supposed to be like some kind of an inverse function. I guess what they're trying to say here. Again, you have to kind of use, once in a while they'll talk about functions in this way. And once again, what this means is, and so, and then they go on to say this function is called the inverse function. Of f, and is denoted by f minus 1. Like this. So once again, what all this is saying is we just have, again, if what we're most used to is a function like this. And so it's really saying, you know, if you have, like, let's say, call this A1, A2, A3, and let's say it's, you know, maybe mapping to something over here, say B1, B2, B3. However this happens to be. So if you put in FA1, you get B1. If you put in FA2, you get B2. FA3, you get B3. Or another way to think of those is the function F is going to be like, you know, something that has like these pairs. Like this. And then, so the inverse function if you put in B1, you get A1, B2, you get A2. If you put in the inverse function B3, you get A3 like this. And then, so your inverse function is just going to be like these pairs, like they're showing here. You're going to put in B1, and you get out A1, B2, get out A2, B3, you get out A3 like this. So that's kind of another way to represent these inverse functions. You're putting in stuff in the, from say the y coordinate and getting out the x coordinate. Though when you write this as an inverse function, of course, now it's the y values, so to speak, that are the domain, and then the outputs are going to be along the x-axis. So that's kind of what that's kind of showing, and it's kind of just sort of a different way. And sometimes it's helpful to represent functions this way with these pairs. And the other thing to note here in this theorem, as we said before, really if something is not going to be one-to-one, it's not going to be really a candidate for having an inverse function, because when you go the other way, you could get two outputs for every one input, so therefore they can't really. And also, I guess, and technically also, it has to be onto as well, because the other thing for a function we don't mention too often is that you have to have some output for every input to the function. In other words, you have to, if you have something in your domain, you have to be able to put something in and be able to get something out. So if it's not onto, then when you do the inverse functions, you can't get anything out for certain values. So therefore, in the cases before, like that we had, if something wasn't onto, so if something wasn't onto, let's say if it was something, let's see. Oh yeah. Now again, we'll probably talk about this later, or you can sort of think of maybe like a. Well, first of all, yeah. Let's see. That gets kind of messy too. But on the same examples, you get sometimes they get kind of messy. But the main thing is, if you want an inverse of a function, you have to be able to take anything from your domain and be able to put it into the function. And if something's not onto, that means there's going to be some values here that aren't available to put into the function. Any questions on any of that? But the main point is it has, simply said, though, it has to be a bijection to have an inverse is what it amounts to. Okay, let me go throughout some more things, more sort of just sort of technical issues here. Let's take a look at it. Once again, just another definition. If f is a function from A to B, and g is a function from B to C, and if the range of f is a subset of D, the domain of G, and that's equal to B, then the composite function G circle F is the function from A into, I use that word again sometimes, into C, defined by, again, we do the circle. This is just that composite. You probably have had that way back somewhere. And that's really just saying that you're going to put values of x into your function f of x, and then put that output into the function g for all x in A. And you'll sometimes see this notation that means just for all. And so let's think about what all this definition says here. So if the range of f is a subset.
Sorry, what is this from A, B into C? What does that mean there?
Oh, wow. Let's see. Oh, yeah. So it's, let's see. Then the composite function is the function from A up here into C over here. So let's see if we can draw this maybe. So we have a function f, and let's say this is a set A, and then let's see what we have. So we're going to go from our set, it says this set goes from A to B. And so this is our set B, so the function f. And so again, this can be, so now this here, though, the function, this could be a subset of B, though, huh? In other words, we're not told it has to be onto. So this over here could be like, say, our f of A, which are like the image of A, could be like in here somewhere. And then our function G will go from B to a set C, like this. So that's sort of, so in other words, you have a set A, this function F goes from, takes stuff from the set A and maps it into the set B here somewhere. Though, according to what this says over here, it's possible this image or the range of the range of F could be a subset of this set B. And then remember, this is the domain of G. Then the domain of G is going to be the set B, and G takes functions from the set B, G, excuse me, from the set B to the set C, like that. And so it'd be sort of a picture, something like that. So therefore, if you take the composite, instead of going this way, the composite basically just going to say, actually, I wrote that wrong, didn't I? G circle F is going to take something from, so let's see, so we're putting values of X into the function, getting something out here, and then putting those values into G. So get something like that. And then this function, so that's what this is saying up here then the composite function, G circle F, is a function that takes something from the set A, because if you look at this here, we're actually just putting in X's from this set A, just putting values of X in here from the set A. And then so it's going to take them from A and eventually map them over into C, like that. So that's actually what the composite function looks like. Is there any questions on that?
So if you had f of g of x, that would take something from C and map it into A.
Correct. That's right. F of C, yes, that's right. Assuming, and again, assuming that all these, the sets that you have the onto properties from each one, that's right. In fact, I think that's sort of what the next thing, that's a good point you brought up. That's going to be what this next thing is going to be. I think, let's see. Yeah, in fact, that's exactly, oh, it actually doesn't say, let me just see.
If I think about it, like if you do f of g of x, so you're starting with the x value for g, which is b, and then that maps into c, which is then.
Oh, yeah, right. Yeah, so right, f of c, right. So you're right. If you do it this way, that's a good point. If you did this, yeah, let's take a look at that. That's right. So if you did this, so you're taking something from B and you're going to map it to C. And right then, assuming that that this, you could put these functions C into A, or into F, then F would go to, once again, probably some subset. So it looks like it, would that go from, yeah, let's see, all depends. Yeah, right. You have to sort of define these, but you're right. You could, would it go from B to C, then possibly to B again? Is that what we're saying? Because it all depends. It looks like, according to this, our function here, our function F takes things into B. Yeah, you're right. Right. That would be the sort of the idea, though. That's right. You just have to kind of verify that everything that comes out of G, you could actually put it into F. That's right. You could actually have something like that. And then also, let me see for the next one. But the main thing is, yes. So let's look at this now. Let's look at the inverse function then. Let's see over here. So this is 1.1.14 theorem. And let F go from, this time it's a function from A to B again. And G goes from B to C. Let those be functions. And let H be a subset then we have G circle F inverse H is equal to F inverse G inverse H. It's this. Okay, let's see now what is this saying? Okay, once again, we'll have the same three sets as before, except we're going the opposite way. So we have this set A, B, C. And then, so this time, be a subset of C. Yes, okay, so we have this H over here. And so now we're just putting in just these values. And I think I'm assuming what they probably stated more. In fact, so if we look at the picture we had a minute ago, for this, we said we're going from, F was taken from A to B, and then it was going to have some image here. Not could be all B, but could be a subset of B. Then those values are going to be being taken to C. And so once again, it could be all of C, or it could be just this, maybe just some part down here. And I think that's in the next thing, what they're probably assuming then that where it gets mapped to is going to be the set H. And then so when they do the inverse function, I guess that's why they're saying H here. They must be assuming probably this isn't necessarily going to be all of C. So now they're putting in these values here. And so now when we go back the other way, this G inverse, if G went this way, G inverse is going to go that way. And then it's going to get mapped back to this set. I suppose once again, it's going to probably be that image of F, and then that's going to then get back mapped again this way. And so it's going to be F inverse like this. So you're just going back the other way with the inverses. Now, what in the book, did they characterize anything more than that? Was that all they said? Yeah, I guess that's all they said. They made that kind of short. So in any case, that's the definition of the inverse. Any questions on that?
So you mentioned like it would have a restricted inner domain of H, but if it's bijected, then wouldn't the entire codomain of C be included in it?
Yes, it would have to be. Yes, if these were both bijections, that's right. If F was a bijection and G was a bijection, that's right. It would have to be everything because when F went from A to B, it would get all of B. And then therefore, if all of B is being put into G, and if G is onto, then it's going to get all of C. That's right. Exactly. That's right. I guess it's kind of odd the way they're not always consistent when they go from one to another. Here, they didn't specify that these were bijections. I guess maybe they wanted to leave it more open to, maybe to other other possibilities, because they actually said here they're saying the range is a subset of B and not necessarily onto yes.
I was thinking just because it was an inverse function, wasn't the requirement to have.
Yeah, you know what? It's kind of really what's kind of odd here is that uh, it looks like the way that they've defined things is that they're on the one hand defining the inverse function has to be a bijection up here, but they're kind of leaving open uh, this down here. And one thing I notice here is that they don't call this the inverse function. They don't call it. I think maybe they want to leave open the possibility that you can still do these sort of things with these sets, even if they're not a bijection. In other words, and then the only now, so therefore, and again, we're going to talk about this actually, I think, in the next section, though it's kind of odd the way they did it out of order here. But so on what we have right here, what we have, if you say that let's say instead of defining it the way we did up here, if we define our functions, let's say f goes from A to, some image of A, we'll just call it, maybe it's something like that, some image of A. And then G goes from that image of A to H like that, then we call that bijection. We're sort of forcing it to be a bijection because we're restricting this set here to be the image of F, which going to make it onto automatically. And then same thing over here. If we're going to put this into it, and then this is going to be image of G, therefore it's going to be onto, right? So if you restrict it like this, that forces it to be a bijection, right?
So they're basically introducing the possibility for domain restrictions.
In the next section, yes, it's kind of interesting. Yeah, it's kind of interesting. I don't know if I suppose probably it's possible they could thinking maybe this was kind of a way to introduce it, though it seems a little bit opposite, but maybe they wanted to put this down first and then say, okay, this is how you do it. Any question? Do you have any questions, Emily, on any of this? Okay, good. Yeah, so in the next section, so let's talk about that, where they do talk about the restrictions. And so then restrictions. If f is a function from A to B, and if A1 is a subset, now they actually use the notation for sort of proper subset. We can define a function and they have a lot of notation here, F1 that goes from the set A1 to B by F1 of X for X in A1. So the function excuse me, the function f1, sorry. It's called the restriction of f to a1. And they mention here sometimes denoted by f1. That's a bit of a vertical. And I don't really see this notation too much, but like this. So, and again, this has sort of a classic example, of course, for as we've been using already. So we consider f of x equals x squared. Note this is not one-to-one, as we already said. But if we define, again, we can call this A1 or A or whatever. I'll just call this maybe A in this case. A equals x's such that x is a positive real number. So in other words, that's going to be the domain now. Then f1, which goes from a to the real numbers, which is f of x equals x squared, is an injection, is one-to-one. And, also, I probably should as well, let me see. Really what comes out of this is also going to be maybe say from a, let's see, the positive real numbers, should I say it this way? From a to the positive real numbers. So then this isn't an injection, so it's one-to-one. And if we say that it just goes to positive real numbers as well, then we could say it's onto, couldn't we? And surjection. And therefore has an inverse. So in other words, if we restrict f of x equals x squared just to the set of positive real numbers, then the kind of function we're going to get will look like this. And it goes on and on and on. Then this then obviously passes the horizontal line test, and also again, if we then set our codomain at the positive real numbers, it's also going to be onto as well. Any questions on that?
So that was two restrictions then in order to make a budget.
Yeah, right. The only right. I wonder the thing. I'm not sure if I'm using the proper term. Yeah, probably. If it what I'm not sure if they use the restriction for like where the range is going to be or not. If they call that a restriction, but I think that's right. Maybe it would be good to say it two restrictions. That's right. I think that would be good. So we're saying that we take values from here and we're just going to map them to the positives. That's right. So therefore, it's going to be 1-to-1 and onto if we restrict it that way. Can you think of like another function that you might want to restrict to make it have an inverse?
You do a trig function like sine of x.
Right, exactly. Trig function. In fact, we actually do that all the time without even thinking about it, don't we? We actually, for example, if you have like f of x equals sine of x, and if you think about what we have, we're going something like this. And really, that doesn't have an inverse. Let's see, either in here, although let's see if we extend it farther. Let's see if we go down this, it repeats here. So really, we want to restrict it somewhere on here so that we don't, so that it's 1-to-1. So what do we have to do really? We have to restrict it from where to where? Looks like we have to restrict it from like minus pi over 2 to pi over 2. Does that look right? In other words, so and so like for example, so what our function, let's say call our function A, or domain, is going to be the x values such that x is from minus pi over 2 to pi over 2, like that. And then if we then so we derive function this way and say it's going to go from A, and actually we should also say maybe B as well. Again, when you sort of think about how we actually do this automatically without even thinking of these restrictions. We've done this probably since high school. It would be better to call these, again, we could call these, let me call these y, so you could really call these x if you want to. I'll call them y just to make it kind of more obvious what we're doing, like this. So if we define our function fx equals sine of x, and then say it's going to go from A to B, where B is from minus pi over 2 to pi over 2, it's going to then look, then it's going to look something like this then, isn't it? It's going to be from like here sort of something like that, huh? That's kind of what our new function is going to look like. And then this has an inverse. And so that's another one where we have, you know, and maybe using it in notation, we want, again, if notation probably not real critical, I just don't call this F, but sort of define what it was from A to B. Any questions on any of that? Okay, if not, let me just go over some. We already went over some. Let me just go over some problems at the end of the section here. And just so that's actually the completion of section 1.1. We've completed the first section here. And let me go over. Let's see. I think I mentioned you guys can look over some of these problems. Let's see.
I was able to work up to the first 4. So.
You did the first 4? Yeah, good. Good. In that case, let's yeah, and those are all pretty similar to the examples we did before. Let me do actually let me do 13. I mentioned that you could eventually try number, did I say number 12?
Yeah, I think so.
Yeah, so let's do let's take a look at, so if you work on number 12, let me go over 13, which is a little bit similar. Okay, 13. And we have to show that F going from A to B and GH are subsets of B. Then the inverse function G union H is equal to the inverse of G union inverse of H. I want to show that. And F inverse G intersection H is equal F inverse G a section like that. Okay, so let's do the first part. Let's do this first part over here first. And we're going to focus on this right here. And just as we said before, in order to show 2 sets are equal, and these are eventually going to be sets because we're putting a whole set, we're considering all the values we're putting into F, all the values you're putting in to B and so forth. And so these are going to be sets. So we'll start with something over here. If X is a typical element in this set, what does this mean? That means since this is an inverse function, there must have been, say, some value over here that you put in here that would have produced that X, huh? So then there exists And I'm going to use this backward capital E. And that means, I don't know if you've had this much before, that means there exists then there exists a Y in G union H such that F inverse Y equals X like this. That makes sense, doesn't it? In other words, if, and sort of keep in mind, it might even be helpful to have a picture so that, let's say, if we have, like, say, F, let's see, we have a function F going this way. F is going to go from, so F is going from A to B like this. And then this G and H are over here, aren't they? They're like over here. And now there's going to be an inverse function going this way. So therefore, if there's a value in X, there's something in this image of these two, then there had to be a Y somewhere in here, somewhere in that union, such that when we take that inverse, it would produce that X. So that kind of makes sense. So, and what does that mean then? So that means Y is in going to be in G and or Y is going to be in H, huh? And so let's see. So further then, to keep in mind where we're trying to head to, we're trying to get this right-hand side. And we almost have it here because if this Y that we're talking about that produces this X is in either G or H, then therefore X has to be in the inverse image of G and or X is in the inverse image of H. Therefore, since in this and or this, then X has to be in F inverse G union F inverse H. And then so we've proved we picked something over here in the left-hand set and proved it was in the right-hand set. So then so far we have F inverse G union H is a subset of F inverse G union F inverse H, like that. See if that makes sense. If that's okay, then we'll do the other side. Let X be in F minus 1G U of F minus 1H. So pick something in the, on the right-hand side. Now pick something in the right-hand side. We want to eventually prove it's in the left-hand side. So once again, if this is true, then X is in the inverse image of G and or X is in the inverse image of H, like that. Therefore, there exists, again, that backward capital E means there exists a Y in G and or a Y in H such that F inverse Y is equal to X. Therefore, so if that Y has to be in G and or H, therefore Y is in G union H, and carrying just we had from the previous step such that F minus Y, and maybe even here, maybe I should also put it there exists here, huh? Maybe I should put there exists at the beginning here, just to make it more proper. So therefore there exists a Y in that union such that's true. And then let's see, such that F of X, let's see. So there exists a Y such that that's real. Okay, and therefore X is in this inverse of G union H, like this. Because if there's a Y in this union such that the inverse produces the X, then X has to be in this inverse here. Therefore, F inverse U, F inverse H is a subset GH union H, like that. And let's see, so we prove this and prove this, so proof is complete. Any questions on any of that? Well, this is sort of kind of following the definition of what everything is. Though it's a lot different than things you've done before, probably. So let me do then the second part, which is, let's see, this part up here. Let me do that now. And so now I want to show that F inverse G intersection H is equal to F inverse G intersection F inverse H. So once again, we'll take something on the left-hand side. Let X be in section H. Then, so in other words, if we let something be in here, then there has to be, then, then there exists, I should say, then there exists a Y in G intersection H such that F inverse Y is equal to X, like that. So in other words, if so we're picking something in that F inverse G intersection H, then that means there has to be a Y in there that produces that X when you go in the inverse direction. Therefore, and notice this is in the intersection times, therefore there exists a Y in G and a Y in H such that that's true. I'll just put ST for such that equal X.
Is it appropriate to use the vertical line or the double dots here for such that?
I've never seen it done that way. No, no, actually, I'm not sure it's incorrect, but I've never actually seen it done. They some I have seen them use the let's see, the reversed small e. So whereas you have this here, I think sometimes they'll use that for such that, which is
Mr. Dambaugh uses that one.
Oh, does he? Okay, he does.
Yeah.
Use this for, okay, good. Then you guys have seen that. So that would be a way. Maybe we should use that then. Yes. So probably something like that. Yeah, that's a good thought. I usually only see the line and the vertical line and the double bars within the set notation you use such that. But that's a good thought. And so now let's see. Yes, so such that f of x equal x. So once again, if this is true, then there exists a y. Then, therefore, x has to be in f of minus 1g, and x is in f of minus 1h, like this. Then, therefore, if this x is in both of these, then x is in the intersection. Excuse me, oh yeah, that's right. Is in the intersection like this. And then, so therefore, we can say that, let's see, what do? We pick something on the left and prove that it is on the right. So we prove that, so F inverse G intersection H is a subset of F inverse G intersection F inverse H, like that. So now going the other direction, we'll pick something on the right. Let X be in the right-hand side set. Pick something is in there. Then, let's see, so then there exists a, let's see, yeah, right, so then there exists a y. And let me say, we have to be real careful right here, don't we? Because, see, this right here, what does this say? This says that x is in the inverse here and the inverse here. So something in G produced the x, something in H produced x. We can't be sure it's going to be the same y at this, yet. We'll be able to say for sure in a minute. We have to be sure. We have to kind of be careful that we don't just assume that right now, because this is a little bit different from what we had before, because these are already separate. So there exists an y1 in G. I should write this down in the next line. Let me write this. Give us a little more room. Then there exists a y1 in G and a y2 in H, such that, yeah, we said we could use our reverse notation, such that f f minus 1 a y1 equals x, and f minus 1 a y2 equals x. But so again, we just have to be careful. But then now, if we think of the context we have, but because the function, because f is a function, right? That means that when we're going from x to here, the other direction, when it went in the from the function f went from the x to the y1, it couldn't produce a y1 and y2, could it? Because, like, say we have this inverse function came from a function f. So what this is almost saying, let me just, I don't want it to put it right down here, but so what this is kind of saying is that f of x equal y1 and f of x equal to y2, doesn't it? So therefore, that's impossible for a function, right? Because for something to be a function, it can only produce one output for each x. So therefore, but since f is a function, we just have one y1 is equal to y2, like that. And we'll just call this just y. And again, in this case, it doesn't matter. But sometimes when we get something like this, you have to kind of be careful, because there's going to be some context when you could have, like, say, an f in this set. You have something in this set and something in this set, but it could have possibly, in another context, been produced by two different things. So we just have to kind of be careful to kind of keep that in mind. So therefore, so that's sort of a side note there. So let's see, where was I headed? And so therefore, there exists a y, and up here we said that y1, y2 were in G and H. Now that's just one y. So there exists a Y in G intersection H such that X is in F inverse of G intersection H, like that. And let's see, so what have we shown? So F inverse G intersection F inverse H is a subset of F inverse G intersection H, like that. And so we proved this one, and we proved this one. So we're done.